This concept of limited supply stoichiometry piggybacks off of ordinary stoichiometry. So ordinary stoichiometry, all it is, and I've written I could write a balanced equation across the board, and all stoichiometric calculations are is going from the amount of something to the amount of something else. That's ordinary stoichiometric calculations. Limited supply stoichiometry means that you have to identify the reactants. It's always going to be the reactants that's there in limited amount. It's the one you're going to run out of first. Okay? The opposite of limited is actually excess. So if you have two reactants, one will be limited, one will be excess, unless, like this says in the italics at the bottom, unless they are both going to run out at the same time. And if that's the case, we say that they are present in the correct stoichiometric ratio needed. Like if you were making a cake and you ran out of sugar and eggs at the same time, okay? But if you were trying to make as many cakes as possible and you were going to run out of sugar first and had plenty of eggs, sugar would be your limited reactant. Eggs would be in excess. Now, if you have three reactants, like we know, we can count reactions can get complicated. If you have three reactants, in general, one will be your limited and the other two will be your excess. So we're going to I'm going to talk you through, we're going to just think through this and just eyeball it. So if we're making some ham sandwiches, for every ham sandwich, you need 2 pieces of bread and 1 slice of ham to make your sandwich. My husband still talks about how growing up his folks were so cheap that they took their pieces of ham and they split them in half. So you need a whole piece of ham, but a half piece of ham. But anyway, so we're making these sandwiches. Can you see where we have 2 reactants? We have bread and ham, and we have 1 product. And actually, we have stoichiometric coefficients. 2 pieces of bread, 1 piece of ham will give you 1 sandwich. So just eyeballing this. We're going to actually we're going to transition this into a chemical equation representing a chemical reaction. But just eyeballing it, if you have 20 slices of bread and 7 slices of ham, which are you going to run out of first?
Ham.
Ham. Why? I agree.
Because if you have 14 slices of bread, you could
Yep. I don't, exactly. They're saying, yep, I bet you guys are thinking we're going to run out of the ham first. And if we used all the ham up, we'd only need 14 slices of bread. Exactly. So let me see if I can find my pen in here. So the ham is limited. We say the ham is limited and the bread is excess. Exactly. You got it. And you already answered these other questions. So how many sandwiches can you make? 7 sandwiches. And actually, this is going to be a trend. This is the way we do it. We focus on, you told me 7. You probably told me 7 because I have 7 slices of ham. And it's the reactants that's there in limited supply that what I say drives how much you get, and it actually is going to drive how much of the other reactants you're going to consume. So related to that, how many slices of bread will we use? 14, I agree. We're going to use 14 slices of bread, and then how many slices of bread will we have left over? Yep, 6. 20, that's a 2. 20 minus 14 is equal to 6, exactly. You guys just did a limited supply stoichiometric calculation. Now I'm gonna actually talk you through what's gonna feel, you're like, Mrs. Science is so intuitive, why are you making it harder? But the process I'm gonna show you is the way I identified that we're gonna run out of ham first. Okay, so here we go. So, I come up with 2 ratios. I have the need ratio, and that's going to be from the balanced equation. Okay, so my need ratio basically says I need 2 slices of bread for every 1 slice of ham. That's my need ratio. 2 slices of bread for every 1 slice of ham. Where did I get it? From the balanced equation. 2 slices of bread, 1 slice of ham. Then the other ratio is what I call the have ratio. So I have the need ratio from the coefficients of the balanced equation. And the have ratio is what we were given. So what were we given? We were given 20 and 7, weren't we? Okay, so that's it. 20 and 7. What were we given? What do we have? 20 slices of bread, 7 slices of ham. If I take 20 and divide it by 7, I'm going to get a number, 2.86. Okay? So what I have is 2.86 slices of bread for 1 slice of ham. What I need, and I kind of tease, I kind of chant it back and forth. This is what I have. What I need is 2 slices of bread for every 1 slice of ham. I have 2.86 slices of bread for every 1 slice of ham. So do you see where I have more than I need with regard to the bread? That's it. Okay? So you compare those two, and like I said, I kind of go back and forth. And this is a quick way, we can do this with chemicals in a chemical reaction. I'm going to scale that up here momentarily. Okay? We came to the same conclusion you guys intuitively came to. Bread is in excess. So if bread is in excess, then ham is limited. It totally is limited. And it's the limited one is, and I feel like in my own mind I put a star next to the ham because it's limited. And like I said, it drives how many sandwiches we make. It drives how much product we get. It also drives how much of the bread's going to be consumed. All right. Okay. So that's what I said. Ham is the star. Ham is the star. We're going to run out of ham first. Can't make more than 7 slices. Excuse me, can't make more than 7 ham sandwiches because we only have 7 slices of ham. Unless we cut the ham in half. Ah, exactly. That's true. So this might seem kind of silly to you. This is these are kind of the little simple stoichiometric calculations. We're going to take the limited reactant, which is ham, unless you cut them in half. But we're going to take the 7 slices of ham, then we're going to come up with a stoichiometric ratio. You guys see where this 1 sandwich per 1 slice of ham came from? This is 1 sandwich will be produced for every 1 slice of ham. I can do that math. So slices of ham, the units cancel, we're left with units of sandwiches, and we got 7. That's what you guys told me. So the other question you guys told me is we're going to use 14 slices of bread, you're right, but here's how this looks using what we know about stoichiometric calculations. We can go back to the equation per se, and we can put 1 slice of ham on, 1 slice of ham on the bottom and 2 slices of bread on the top, coming from the balanced equation. So units of slices of ham cancel, we'll have the slices of bread. Of course, 7 times 2 is 14, and that's what you guys told me too. So I'm kind of showing you how we can apply the tools that we've already kind of been talking about using the limited reactant. Okay, so then the last thing we're going to do is say how much bread is left over, and that's where you saw me take my 20 minus my 14 to give me 6. Okay, and that's kind of a classic sort of set of questions that we're going to change it up. It's not going to be bread and ham and sandwiches here and there. It's going to be actually chemicals. But we're going to apply some classes. Okay. Now, okay. Okay. So I'm not going to necessarily take the time to go through this, but the caption for this is kind of, instead of sandwiches, what we're making is we're collating a report over here. This is our final report. Our report needs 1 title page. It needs 1 sheet of instructions. The green right there, it needs 2 of those. Those are your data sheets. And the little graph paper here, purple thing, it needs 4 of those. So that's kind of the recipes written over here in the far right. Underneath is kind of the have amounts. If you were to go through a similar process we just did, you would see that you can only make 82 complete handouts, and the thing you're going to run out of first is the graph. So feel free to kind of kick that around. I want to kind of get to a problem. All right, so the problem we're going to pick on, and we're going to look a little closer at this, is this one. I believe it's one method of making ammonia is called the Haber process. It's kind of a famous sort of process. Ammonia is an important thing when it comes to fertilizer and all that farming. But ammonia, the formula for ammonia is NH3, and we make it from just elemental nitrogen. Of course, it's a diatomic element, so it's N2. Hydrogen is a diatomic element, so it's H2. So when we combine those, we're going to take 1 mole of N2 to react with 3 moles of H2 to give us 2 moles of NH3. So that's balanced. We're going to take this through limited supply stoichiometric calculation. Here's a little video. Let's see if it works for us. Kind of had a video we just watched. So that's before. I just think that's so cool. They kind of break up with the atom they have, and they break that bond, and then new bonds are formed as they form ammonia. So yep, the blue are left over. So blue is an excess. Nitrogen is an excess. And back. So here we go. Looks like we're the white again are the hydrogens, and the green here are chlorines. And we're going to actually combine H2 and Cl2. This one's kind of, you could just, what do you think? So they combine in equal amounts. So 1 mole of H2 plus 1 mole of Cl2 goes to form 2 moles of product. So if we have 6 moles of H2 and 4 moles of Cl2, which one are we going to run out of first? I think the Cl2. That would make the H2 in excess. So yeah. So this is kind of showing you, of course, the product is the HCl, and you can see, yeah, we have extra H2s left. Yep. So again, just like I said with the ham sandwiches, the one that's in limited supply, in the case of the ham sandwiches, it was the ham, not the bread. But we took the amount of ham and we found out how many sandwiches we could make. We took the limited reactive ham and found out how much bread we'd have to use. Okay, so the limited one is the special guide. So on your unit, your exam for this unit, your Unit 2 exam, let's see how it goes. I will not make you identify the limited reactant and then go to use that information to work a stoichiometric calculation. So on your Unit 2 exam, I'm going to have you do some simple stoichiometric calculations where you're going from the amount of something to the amount of something else. And I'm not worried about, I will tell you something's in excess. Okay? And though, on your Unit 2 exam, I will have you, and you can't guess, you have to show me why. And there's actually a couple other ways you can identify a limited reactant. But you have to tell me which is the limited reactant. Okay? All right, so let's go back to this chemical reaction between nitrogen and hydrogen to form ammonia. Now we talked about balancing equations. I could have put a brick wall right there at the reaction arrow and find out I had the same number of nitrogens and hydrogens on either side there. So that's balanced. Only if it's balanced can we go ahead and proceed. So, you know how I like to do, I like to take, the reason I like to do it this way is because my eyes go wonky sometimes and I can't tell what's what. So I'm going to put have, the number have, there's the word have up here. With regard to nitrogen, you're talking about 72.0 grams. And with regard to hydrogen, you're talking about 22.0 grams. All right, those are my have amounts. Now, I wish we could just do a ratio of masses and compare my have ratio of masses to my need ratio from the balanced equation, but we can't. So this is to say that I'm going to actually have to convert those grams into moles in a minute. So we're going to answer a series of questions kind of like we did with the ham sandwiches. Which is in limited supply, which is in excess, and you can answer that, no guessing. You have 50-50 chance of getting it right, but you have to put a bunch of gobbledygook to show me how you guessed it. which is in limited supply, which is in excess. And then only after you answer the first questions can you answer these other couple of questions. So of the thing that's there in excess, how much will be left over once the reaction is done? It's kind of like how much bread will we have left over? And then a follow-up question is what will the mass be of the ammonia? Okay, that's like how many sandwiches we've got left. Now we definitely have some, like I mentioned before, we definitely have to go back and forth between grams and moles and grams here. But you guys are getting some practice at. So if you don't already have it open, I want to see your notebooks open, and this finally is where you probably just humanly write your lab note not in your notebooks. So do you guys already have these molar masses? Mm-hmm. Okay, good. So these are molar masses. These are going to be our tools. We just use the periodic table to knock these out. So in order to come up with a half ratio of moles of reactants, I got to take those masses and convert those masses into moles. So on the previous slide, for instance, you had the molar mass of N2 is 28.0, thank you, 28.02 grams per mole. Go ahead and multiply that by 72.0 grams, or a ratio of that, and get to moles. I'm going to put it up on the board. That's our moles of N2. We're going to do a similar thing with the H2. We're going to take the grams, 22.0 grams of H2, use the molar mass, which is 2.016 grams per mole. We're going to use the flipped version of that, 1 mole of H2 over 2.016 grams of H2. Units of grams of H2 cancel. Rounding to 3 sig figs, you're looking at 10.9 moles of H2. Now, I'm not going to flip back through my slides, but if I were working this problem out, probably under those grams where I said have and I had the mass of the N2, the mass of H2, I probably would grab these moles maybe and maybe put them underneath there just because I'm like, oh, isn't that lovely? I converted the mass to moles. Okay. So now the next step is to come up with the have ratio and the need ratio and compare the two. So here we go. We get the need ratio from the balanced equation. And I usually kind of say, I'm into like numbers that are bigger than 1. So what you're going to see is I'm going to put 3 moles of H2 over 1 mole of N2. Now, I could have put 1 mole of N2 over 3 moles of H2, and that would have been fine too. But whatever order I take them in, now that's going to be how I order my have, H-A-V-E, have ratio. So here we go. My have ratio, I'm going to use those moles that we came up with on the previous slide. So what we have from the grams to after getting to moles, what we have is with regard to the hydrogen, you have 10.9 moles of hydrogen, and what you have with regard to nitrogen is 2.57 moles of nitrogen. Now I go ahead and put 10.9 divided by 2.57, and you should get 4.24. And the units of that ratio, we just carried over, so it'd be 4.24 moles of H2 per 1 mole of N2. And this is where I kind of, like I say, I kind of chant it. I need, I have, I need, I have. I need 3, and I have 4.24. Need 3 what? We have 4.24 what? Hydrogen. Okay, moles of hydrogen. So I have more hydrogen than I need. Okay, so how many people think hydrogen is in limited supply? How many people think limited hydrogen is an excess? Excess is 1 out. Yes. Very good. So now I know it feels weird because we're like hydrogen, yay, hydrogen. But this is where now I would put a star next to the nitrogens. I would put a star next to the nitrogen because I'm going to finish the problem using that. It's limited supply. Okay? So my nitrogen is my winner of the day. Okay? Because you're going to focus on what's in limited supply to go ahead and finish answering questions. Yay! Okay, now let's see what we got. Yep, based upon those two ratios, we have more H2 than we need, so N2 is in limited supply. And so on your test, I'm going to be looking for, well, it depends on what kind of mood I'm in, but I will definitely be looking for you identify the correct limited reactant. The reactant is there in limited supply. And I will also be looking for some gobbledygook of how you got there, if you call that gobbledygook. Okay? So we still have a few questions to answer. So one was, of the things that's there in excess, which is hydrogen, how much do we have left? Well, we need to knock out the mass that reacted. So to knock out the mass that reacted, we need to focus on what's in limited supply, which is our nitrogen. So can you see, we've been doing some stoichiometric calculations in here where we go from the mass of nitrogen to the mass of hydrogen. But notice I'm not going to start clear back at the mass. I'm going to start with the moles of nitrogen because I had it a few slides ago. It's kind of a different type of, it takes a little bit, makes it a little easier. And then I'm going to use a stoichiometric ratio. So down here is my balanced equation. If I want moles of N2 to cancel, let be left with moles of H2. What does that ratio look like?
3 over 1.
3 over 1. 3 moles of H2 over 1 mole of N2. Perfect. And so moles of N2 cancel, I have moles of H2, so how can I get to grams of H2? When in doubt, it's the molar mass. Yep, so a few slides ago, the molar mass of H2 is that 2.016 grams per mole. So we're going to put 2.016 grams of H2 over 1 mole of H2. Units of moles of H2 cancel. We have grams of H2. How many sig figs?
3.
I'm liking 3. Yep. Okay, so you're looking at 15.5 grams of H2 reactant. You're like, oh, yes. But that's not quite the question. It's on the way to the question. We're one step away. How do we get grams of H2 remaining? Just subtract. Yep. You got it. So a few slides ago, we actually started with the 22.0 grams of H2. And from that, we subtract 15.5 grams of H2 is what we reacted with a limited reactant, N2. So we don't do a lot of subtraction. Do you guys remember when we subtract, is it decimals or sig figs? It is decimals. And how many decimals are we allowed? Just one. Yep. So that's why it's 6.5 grams of H2 left over. So this would be like our bread left over. And we're almost done. See, there's all sorts of follow-up questions. The last question is, how much NH3 grams? How many grams of NH3 were produced? Well, I'm telling you, my first term is going to be the moles of N2. Okay? Because N2, because it's a limited amount, and moles, well, why would I start with grams of N2? Because then I have to use the molar mass of N2, the moles of N2, and I'm back to here. So now I'm ready to go from moles of N2 to moles of NH3. So what does that stoichiometric ratio look like?
1 mole of NH3 over, 2 moles of NH3 over 1 NH3.
Yep. It'd be 2 moles of NH3 over 1 mole of N2. Yep. Moles of NH3 cancel. We're left with moles of N2 cancel. We're left with moles of NH3. So how are we going to get to grams of NH3? Molar mass. When in doubt. That sounds like a t-shirt. When in doubt, it's molar mass. Okay, so a few slides ago, we knocked out the molar mass of NH3 as 17.03 grams per mole. So that'd be 17.03 grams of NH3 for 1 mole of NH3. How many sig figs? 3. Yep. So I get 87.5 grams of NH3. Phew, and that's it.
So like on a test, do we have to put grams of NH3 produced?
No.
Just
Right. Yeah, you don't have to. Okay. All right, so choices. And actually, if you were taught somewhere else, you might not have been taught this have, need, ratio, comparison thing. So here's a couple of other ideas for you. And some students actually, when I go to grade this on their test, they're like, they did one of these other ways. And they make sense to me. So for instance, we could do this one. There's 2 ways. You could select one of the amounts and do a stoichiometric calculation. Say you have 2 things, 2 reactants. You could say, okay, so if I use all this up, how much, I'll call this A, how much of B will I need? And then based upon your results, you could make a judgment call which one you're going to run out first. You definitely could. That'd be 2 stoichiometric calculations. This other one, again, would be 2 stoichiometric calculations. So if you have A and B reactants goes to form products, you could say, okay, if I have A, how much products am I going to get? Or how much, pick one of the product. If I have B, if I use it all, how much of that same product am I going to get? And then you could compare the masses of those 2 scenarios and see whichever one you have least amount of. And that would show you that the ones that supply reactants. So there's definitely some options. So these Alta homework are due on Thursday. So be here before you know it. And like I said, I think we're in good shape. I'm going to knock out part 8, which is also due on Thursday.
yeah, they're grouped together.
Okay, yeah. Yep. So let's see what we got here. So part 8.
I remember this.
So this is all kind of related to stoichiometric calculations, okay? So percent yield. Now before we get to the percent yield problem, I want to talk about a little bit about what percent yield is. In order to understand percent yield, you have to understand theoretical yield. And actually, on Thursday's lab, just the other day, next to a few, maybe all of the stoichiometric calculations, I might have put theoretical. So whenever you're doing a stoichiometric calculation, I'll kind of put something generic. So we have 2 reactants, reactant 1, reactant 2, goes to form product. I'll just say there's only 1 product. Whenever we do a stoichiometric calculation, so for instance, say we know the grams of this, and we're finding the grams of this. That is a theoretical yield. It's theoretical because you're like, well, if I have this mass of R1, what mass of product am I going to get? That's theoretical. It's like paper and pencil. It's a yield because it's a product. So a special type of stoichiometric calculation in which you're going from the mass of a reactant to the mass of a product, that is giving you a theoretical yield. Okay, so I'm going to talk you through, and I'll go ahead and say straight up, your Unit 2 exam, I'm probably going to ask you questions, so you can put a star and say exam on there if you want to. I'm going to ask you, since stoichiometric calculations are all about knocking out theoretical yields, why in the lab, why in the heck don't we get what we should theoretically get in the lab, the masses? I'm going to talk you through these 4 reasons, and actually each one of these 4 reasons are biased low. So these are 4 reasons why what you get in the lab, we call your experimental results, your actual results, is lower than your calculation, a theoretical amount. So first one is reaction kinetics. So one of the things that we are all such impatient. It's interesting how I think the generations as we go along, we're getting less and less patient. We are very impatient. We think that chemical reactions will happen right away, but they don't necessarily. Chemical reactions, and actually in general chemistry too, that's one of the topics we focus on. It's like, how long do reactions take? You know, because it's a player. So this is to say that if, I'll show you this, okay? This is showing you basically along the x-axis is time. So we have 30 seconds, which is still pretty short. But what you're looking at is the red line is showing you your reactants going down. Oh, by the way, then along the y-axis is concentration. So along the y-axis is showing your concentration going down over time. And then the green one is showing your products. I said that. Your reactants going down, your products going up. Okay, so what this says, like the caption says, if I were to go ahead and stop it about 7 seconds. So we have 2, 4, 6, and so 7 seconds is right about here. Notice 7 seconds actually is where we have about half of our reactant left, and we have half of our product formed. Okay, so our reactants are on its way to form products, but we have about half and half. So if we were to basically squelch the reaction at 7 seconds, we have 50% yield. You know, and sometimes it's inherent in the reaction, and that's about as good as you can get. But this is showing you how long it takes and how long you're allowing the reaction to occur can shorten your yield. Okay. Another topic we cover in general chemistry too, and actually for those of us who really count on acids and bases, and it's a biological thing. Acids and bases really at the crux of those are what we call some sort of chemical equilibrium. I'll pick on this reaction. The reactions we're worried about in Gen Chem 1 go one way. They go from left to right. But there are definitely a lot of reactions out there that also go from right back to left again. And what you're going to see here are 2 arrows. And actually they're called equilibrium arrows. Equilibrium. Okay. I'll just call them equilibrium arrows. So it goes from left to right and right to left again. Well, my gosh, if you're trying to isolate your product, can you see where some of your product is going back to form your reactants again? It's just not happening. Okay, there are a lot of chemical equilibria out there. So this is an example of a chemical equilibria. So we have H2 reacting with I2 to form HI. Okay, so again, we have time along the x-axis. Along the y-axis, we have concentration. So you can see for this particular scenario, we have all H2, I2, and no HI. Give it a little bit of time. Some of that H2 and I2 are going to be converted to HI. But can you see where if we let it go forever, okay, we're still going to have some reactant left, H2, I2, and so our product kind of maxes out. That's what we call chemical equilibrium. All right, here's another one. So the other day when you guys reacted magnesium in your crucibles to form magnesium oxide, if you read the background, there was actually a competing reaction between magnesium and nitrogen to form magnesium nitride. So again, you can't win. It's what I say inherent in that case, the chemistry. Okay? So you're not going to get it all in the form of magnesium oxide. Here's one. Again, I use the word inherent. Inherent means just baked in. So an inherent problem is just you can't do anything about it. Losses that you can't do anything about. So, for instance, especially in organic chemistry, you're going to be doing some cleaning up of your product. And so that for every cleanup step, you lose some product. So there goes your yield, but it's inherent in the experimental design. But honestly, thank goodness for for cleanup, for purification steps, because as you might imagine, when it comes to pharmaceuticals, they're not gonna let you ingest something that's gonna have impurities in it. So it's kind of a trade-off. The more you purify something, the more you lose your product. Okay. So with all that said and done, we have a lot of ifs. So you would get 100%. Let's go ahead and turn this back into a regular equation. You would get 100% yield if, if all of the limited reactants actually went ahead and reacted, and if there was no other side reactions, okay, and if you were able to isolate all of your product, then you're looking at 100%. Okay, so that's not quite the way it works. Okay, there's a lot of ifs. Let's see what I call it. So I have a slide called physical losses here. I want to contrast physical losses, which are inherent in your experimental design, with what I call the oops or the crap, or you can use a different expletive if you want to. The shoot, yes. So actually those are called gross errors, and there's different types of gross errors, but they can also give you wrong yields. Okay. The word is inept, and I kind of feel bad because I'm not perfect, so I can be inept. But it's due to the ineptness of an investigator. So for instance, if you spill something, it would be bias low. Now actually this could be bias low or bias high. If you misread a number, put it down wrong. I've seen a few of those in there. But I've done it too, so that's okay. No one died, so. Or if you make a mistake with your calculation, again, those could be high or low. Not following instructions, okay? So now we're finally to the point where how are we going to knock out a percent yield problem? So percent yields are simply what you actually got back, and sometimes I'll call this experimental. Actual yield, i.e. experimental. And you divide it by your theoretical yield. And remember where you get that from. That's from a stoichiometric calculation. That's it. So when you see this problem on the test, remember how that works. So to get it parts per 100, we're going to go ahead and multiply by 100. Notice, like it says in italics down here, that the units of grams of product you actually got divided by grams of product you thought you should get, those units cancel, and so this makes it what we call unitless. So let's do a problem. Goodness, seems like forever ago, but I think this was Friday. We said that if you have 1.25 grams of Cl2 and you have excess, now you know why we say excess. So your Cl2 is in limited supply, you have plenty of P4. We said that we did a stoichiometric calculation, you should get 1.61 grams of PCl3. All right, well, that's not the problem. It says that what you actually got was, so this is theoretical, you guys okay with that? Theoretical. And the actual is 1.08 grams. So you're a little bit low, that's okay. And again, sometimes people look at those years and like, dang, you did awesome, because there's all sorts of things going on. So simply, all we need to do is plug in the 1.08 grams that we actually got, divided by that 1.61 grams, which we thought we should get, and then multiply it by 100%. And we're definitely going to give ourselves 3 sig figs, so you're looking at 67.1% would be your yield, which, like I said, might be something to go out and celebrate. Okay, so yeah, they're together. Both limited supply and percent yield are together. Those are both 2/3. Yes, ma'am.
Percent yield, do we have to write actual and theoretical?
No, you don't. Megan's asking, do you need to write actual or theoretical, that ratio? No, you don't have to show me how you're doing it, but you need to know how you're doing it. When I work it out, depending on what mood I'm in, I sometimes go ahead and write that down, and then I have it down there I can plug in, but you don't have to. Just make sure you get them right. Okay, cool. So we're set. I'm not sure on Wednesday if I want to go into solution concentration, probably. I know there's still hydrated salt I need to get back to, but I think I'm probably going to try to get to molarity on Wednesday, so then it'll be better for your topic on Thursday. And then probably hydrated salt on, stick it in on Friday probably. And that's not going to be an Alta homework. I'm actually going to give you a paper copy of that part. All right. That's it, Mom.